Here is an AR2 model for which I'm wanting to find the general expression for rho sub k and rho sub 4. I'm going to use the inverse of the roots of the characteristic polynomial in this problem to find the general expression for rho k. So I have x sub t minus 0.7, x sub t minus 1 minus 0.15, x sub t minus 2 equals a sub t, which is xt minus 0.7 b times xt minus 0.5 b squared times xt equals at, which would give me 1 minus 0.7b minus 0.15 b squared equals a sub t. The characteristic polynomial here would be phi of b equals 1 minus 0.7b minus 0.15 b squared. I could also rewrite this as phi of s equal to 1 minus 0.7s minus 0.15 s squared. So I want to find the roots of this characteristic polynomial, so using the quadratic formula, the roots end up being minus b plus or minus square root of b squared minus 4 times a times c divided by 2a. And if you use the formula, we'd end up finding the roots as 1.147 and negative 5.813. Both roots lie outside the unit circle, which would imply xt is causal and stationary. So since the roots are 1.147 and negative 5.83, we would have the inverse of the roots to be 1 over 1.147 and alpha 2 equals 1 over negative 5.813. That would give me alpha 1 equal to 0.872 and alpha 2 equal to 1 divided by negative 5.813, which is negative 0.172. So since we have the values of alpha 1 and alpha 2, the general expression for rho k is alpha 1 raised k plus 1 times 1 minus alpha 2 squared minus alpha 2 raised k plus 1 times 1 minus alpha 1 squared divided by alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2. So we have 0.872 raised k plus 1 times 1 minus 0.172 squared, which is 0.9704, minus negative 0.172 raised k plus 1 times 1 minus alpha 1 squared, which is 0.2396. And we divide that by alpha 1 minus alpha 2, which is 1.044, multiplies by 1 minus 0.872 times 0.172, and that is 0.85. So we have 0.872 raised k plus 1 times 0.974 minus 0.172 raised k plus 1 times 0.2396 divided by 1.044 times 0.85. And that is 0.8874. So we end up having 0.872 raised k plus 1 times 0.9704 divided by 0.8874, which would be 1.094 approximately, minus 0.172 raised k plus 1 times 0.2396 divided by 0.8874. Which would give me 0.27. So that is the general expression for row k, and I've found this simply by using the roots of, or the inverse of the roots of the characteristic polynomial. Mind you, this only works for an AR2 model, not for any other model, just AR2. And we derived this expression right here for AR2. Excuse me. So row k ends up being that expression. Now that we have a general expression, we can find row sub 4 by plugging in 4 for k. So we have 0.872 raised 5 times 1.904 or 1.094 minus 0.172 raised 5 times 0.27. That is 0.5515 minus 4 times 10 raised negative 5 with a negative, so that becomes positive. That number is quite small, so row 4 would simply end up being 5515. So that is how we find the general expression for row k without using the difference equation, rather simply using the inverse of the roots of the characteristic polynomial. So here is another example. we want to find the general expression for row k in an AR2 model with row 1 equals 0.7825 and row 2 equals 0.3027. Also, we are going to find find row 2. So row 1 is 0.7825, row 2 is 0.3027, and we do not have phi 1 and phi 2 in this problem. So our first objective is to fit the model. So how do we find phi 1 and phi 2? So we make use of the Euler-Walker equations. In the matrix form, we would simply have row 1, row 2 equals row 1, 1, and 1, row 1 times phi 1 and phi 2. Which in this case would simply end up being 0.7825, 0.3027 equals 0.7825, 1, 1, and 0.7825 times phi 1 and phi 2. So I'm going to call that matrix A and call that B, which would imply phi 1, phi 2 is equal to B inverse times A. I'm going to show you how to do this using the calculator. I'm going to press the matrix button. I'm going to first define matrix A. I'm going to edit. There are 2 rows and 1 column. So A is 0.7825 and 0.3027. And we have to define the matrix B. It is a 2 by 2 matrix. Whoa. And the values are 0.7825, 1, and excuse me, I have this backwards. It's 1, row 1, and row 1, 1. So that would be 1, 0.7825, 0.7825, and 1. So now all we have to do is find the inverse of B. So I select the matrix B. I'm going to type inverse and select the matrix A and enter. I end up getting phi 1 and phi 2 equal to 1.407 and negative 0.7985. So the fitted model, or the model, is xt minus 1.407 xt minus 1 plus 0.7985 xt minus 2 equals a sub t. So now we've got defined the characteristic polynomial. The characteristic polynomial is phi of b, which is equal to 1 minus 1.407b plus 0.7985b squared. I could also write this as phi of s equal to 1 minus 1.407s plus 0.7985 s squared, just to keep things simple, I guess, even though it is not necessary to go from b to s. So we have to use the quadratic formula, and if you use the quadratic formula, we are going to get complex roots in this problem. Oftentimes, if we have phi1 to be greater than 1, so we have phi1 to be 1.407 and phi2 as negative 0.7985. Typically, phi1 is greater than 1. It is more than likely that we are going to end up with complex roots. So using quadratic formula, the roots are R1 or S1 equal to 0.8812 plus 0.69i, and R2 is simply the conjugate, so 0.8812 minus 0.69i. We have to find the inverses of these two roots, so 1 over R1 is 1 over 0.8812 plus I times 0.69. We have to rewrite it in terms of a complex number, so I'm going to multiply and divide by the conjugate. Which would end up giving us .8812 minus I times 0.69 divided by 0.8812 squared plus 0.69 squared. So alpha 1 is 0.8812 divided by 1.253, which is 0.7033 minus I times 0.69 divided by 1.253, which is 0.5507. So if alpha 1 is 0.7033 minus I times 0.5507, naturally alpha 2 would be equal to 0.7033 plus I times 0.5507. Here I'm going to call that A and I'm going to call that B. So minus v2 divided by r. Let's quickly check that. I believe it is minus v2. I would like to check that. It's actually a over r. And the value of a is 0.7033. And the value of r is 0.8932. And cosine inverse of the answer and divided by 2 times pi. Which gives us the system frequency as 1.043. It simply means that in the periodogram there will be a peak at 1.043. So now we have an expression for rho k, which we derived a while ago, which is rho k equals square root of negative v2 raised k times sine 2 pi f naught times k plus 1 minus sine 2 pi f naught times k minus 1 divided by one minus v2 times sine 2 pi f naught. So we have f naught to be 1.043, so it would simply mean two pi f naught is 2 pi times 1.043, which gives us 6.553. So rho k would now equal to square root. We derived v2 to be negative 0.7985. And negative of negative would become positive 7985 raised k times sine k plus 1 times 2 pi f naught is 6.533 or 6.553 minus sine k plus 1 or k minus 1 times 6.553 divided by 1 minus v2 is 1 minus of minus 0.7985 times sine 6.553. Keep in mind here the sign is in radians, which is why we have 6.553. We are using regular xy coordinates. So square root of 0.7985 is 0.8935 raised k times sine k plus 1 times 6.553 minus sine k minus 1 times 6.553 divided by 1 plus 0.7985, which is 1.7985 times sine 6.553, which is 0.4793. That is our general expression for row K. Now we simply have to find row 4. So if we plug in K equals 4, which would imply row 4 is equal to 0.8935 raised 4 times sine 4 plus 1 is 5, 5 times 6.553 minus sine 5 times, 4 times 6.553 divided by 0.4793. And we end up getting row 4 equals 0.1249.